Okay, hi everyone. Yeah, I'm Dr. Manmohan Singh from Dr. Laren's Biomedical Optics Lab. Sorry he couldn't be here, but he's traveling right now. And so I'm going to talk about the engineering principles of optical coherence elastography. And thank you to Dr. Roberts, who's been such a wonderful champion for our field. So you guys kind of understand, get a great introduction of the importance of what we're working on here. So I'm just going to go really briefly and really quickly on some of this stuff. We really Dr. Roberts did a great introduction of why we want to image mechanical contrast in the cornea. But overall, in general, we understand that diseases alter the biomechanical properties of tissues. That's why Hippocrates created the physical exam to try to feel for those different, nodules and stuff. And of course, we have that with the cornea, where we created the corvus and the ORA, where we can measure these biomechanical properties of the cornea. But what if we want to go deeper? And what if we want to go, with better resolution? So in the early 90s, the field of elastography was created using MRI and ultrasound imaging. And so this is a wonderful example of one of the kind of killer apps of magnetic resonance elastography. You can see in the top row, we have a liver, and we have on the left the MR image, and this is the waves being created in the image in B. And in C, we have the elastogram, or a map of the stiffness of biomechanical properties. But in D, we have another patient who had a cirrhosis of the liver. And so you can see in the structural image, it looks the same. However, in the mechanical image, there's a clear indication that there's some fibrosis or fibrotic scarring going on in this liver, even though the structural image is the same. So that's what's really important is first we have to think about how are we going to quantify the mechanical properties of the tissue. So the most common parameter that you'll always see is what's called Young's modulus or the elastic modulus, which is often written as E, which is basically how much does the tissue deform when we apply a known pressure. And so that's just the force divided by the area, which is the stress. And then we measure how much it deforms by measuring the change in length divided by the original length, which is the strain. You'll often see written as sigma epsilon. So we have to remember the stress divided by strain. This is basically the uniaxial measurement of stiffness. And so we're going to use optical coherence tomography, and I'm sure everybody here is pretty familiar with it, so I'm not going to go into OCT, because we want to measure tissues. And so we're specifically talking about ophthalmological applications where we have kind of thin, maybe, I don't want to say delicate, but due to their geometry, shape, and structure, and kind of the resolutions that we're seeking, it's very difficult to use the clinical medical imaging techniques such as ultrasound imaging and magnetic resonance imaging. So OCT provides us a wonderful way to map these biomechanical properties. But one of the most interesting questions that we have is how do we apply this force? Because in elastography, what we do is we have an imaging modality, we apply a force, we measure what the response of the tissue is to that force, and then we link it to a material parameter through a mechanical model. But in the cornea and the other eyes in the tissue, how we do the excitation is really, really critical, not just for safety concerns, but also for the mechanical modeling, because we have limitations, which I'll go into a little bit later. So these are all various image excitation modalities we have. And most of the time, the excitation modalities are split up into two areas. We have contact and non-contact. And especially for ophthalmological applications, we tend to focus heavily on non-contact methods just for comfort and ease of use. And if you're more interested, you can read this review paper by Dr. Laren and Dr. Sampson in 2017. And then the elastography itself is kind of split up into two modalities. We have static or quasi-static techniques where you basically take an image, you squish it, and then you take another image, and then you look at how everything inside has shifted. And then you can map what's called the strain. And then if you know the force, you can map the Young's modulus, and you can get what you saw earlier, which is an elastogram or a map of stiffness. And then there's also dynamic techniques, and most of these rely on the propagation of waves or some type of vibration that you induce in the tissue. And then from that, you can get the mechanical properties of the tissue. So I'm going to start here with dynamic techniques here. So most of these are wave-based, as I said earlier, and you can see here in the video on the bottom where we're exciting a wave in the middle of this phantom, which is soft on the left and stiff on the right. And by converting the wave speed into the shear modulus or Young's modulus, we can then get a map of the stiffness. So we see here that the wave speed in the left is about 1 meters per second, and the wave speed here in the right is about 4.5 meters per second. And what's important to note here is that in the wave speed to the modulus conversion is actually a square law. So even though these are about 3.5 times faster, like 12 times, they're actually 12 times, the stiff region is actually 12 times stiffer than the soft region. So you can see that even easier here in 3D, where we have one soft phantom on the left and a stiff phantom on the right. You can see this wave propagates much faster in the soft, much slower in the soft phantom, and much faster in the stiff phantom. And so what are these applications of ophthalmology? Of course, we're here for all that. And so one of the main diseases that we work on is keratoconus, but there's also implications in presbyopia, and I'll show a little bit of our results on that, and also glaucoma, where we can see if there's any damage caused to the retina specifically. And there's a lot of interest right now in glaucoma in looking into the biomechanics of the trabecular meshwork and how it regulates the fluid flow. So here's just kind of a demonstration of that. Here we have an elastic wave being induced in this cornea here. And you can see that most importantly for us is that this displacement, you can see it on the scale of micrometers. So we're not causing any disturbance to the entire eye globe when we're creating these waves that are propagating through the cornea. And so we'll go into a little bit later and deeper how we can convert all of these properties into actual parameters of stiffness in the cornea. So one of our first studies that we worked on using this was to actually measure the change in stiffness in the cornea due to cross-linking. So cross-linking, we all know, is designed to make it stiffer, but how much stiffer? So most of the techniques previously were using mechanical testing, but that's not really how the cornea behaves in its curved shape in the eye globe with intraocular pressure. And so we see here that the wave speed increases quite significantly after cross-linking in both, these are paired eyes. And it's quite significant, going from about 1 meters per second to a little bit more than 3 meters per second. And so you can see that again here in 3D. You can see this wave propagating in the left eye. These are porcine corneas in situ and at a controlled eye intraocular pressure. And so on the left eye, this wave is propagating slowly, which is the untreated eye. And then after we cross-linked it, you can see that the wave propagates much more quickly, which of course means it's stiffer. Now, beyond just looking at the speed of the wave, we can also do what's called spectral analysis. So because of the shape of the cornea, it's basically a curved thin plate, is that these waves will disperse, or basically each of their frequencies are going to travel at different speeds. And using those properties, we're actually able to map the changes in the cornea, to map the changes in the biomechanical properties of the cornea as we go down through its depths. And one of the coolest applications we did using this was to actually determine how deep the cross-linking is actually happening using this, what we call the phase velocity, or the speed of the wave at different frequencies. And so that's what we see here is we did a comparison study comparing UV cross-linking versus green light cross-linking. And what we see with UV cross-linking is that's actually penetrating almost approximately a third into the depths of the cornea, which is almost or pretty much the same as we've seen from other studies using Brion microscopy and ultrasound. But also that green light cross-linking, which has been proposed as a safe alternative with non-ionizing radiation with the UV compared to the UV, is it was actually only cross-linking about 1/6 of the anterior of the cornea. And so because of that, overall in the study, we found that the green light cross-linking was not increasing the stiffness of the cornea significantly. So one of the limitations we have with using our air puff that we were using, it's a focus micro air pulse, is that it has limitations in bandwidth, which I'll discuss a little bit later too. And so what that means is that our contrast in the wave speed from the anterior to the posterior of the cornea is very low. So Fernando here, Dr. Zviatkovich, has created this kind of octopus thing to it just touches the cornea, and then it's attached to this piezoelectric bender, and it vibrates, and it creates this reverberant field. And using that, he's able to map the biomechanical properties of the cornea down through its thickness with much greater degree of contrast. And so you can see here, for the example of green, this solid line here is actually, if we use the technique we saw earlier, but using his technique, he's actually able to show much greater degree of contrast. And so, of course, we've been working on this technology for almost maybe a decade. Yeah, close to a decade now. And so we started our pilot human studies. And this is Dr. Twa here with their clinical system that we've got set up, and we're show some of the results from our pilot human studies. And so what we see here is the wave propagating through the human cornea, and we have 9 subjects here comparing. These are all healthy subjects, so it's just validation. And kind of this is how the wave looks like as it's propagating through the cornea. And one thing that we notice, of course, is that there's a correlation between the intraocular pressure and the wave speed. And this is pretty well known because the cornea is very nonlinear. So as the intraocular pressure increases, the stress on the cornea increases, the strain increases, but that curve is not linear. So as you move further up the curve, it's kind of shaped like a J. And that slope of the line is the modulus that you're measuring. And so as we move further up the curve in the cornea, we get a higher modulus and a higher wave speed. And so as I discussed, one of the limitations we have with this focused micro air pulse is its actually ability to create high frequency waves. And in the cornea specifically, we want to reduce the influence of low frequency waves because they actually get influenced by the boundary conditions, which I'll talk a little bit later too. And so we want to introduce a way to create high frequency waves so we can have more robust and more accurate estimates of elasticity. And so you can see why that's important here is that as we increase the bandwidth, not only do we reduce the influence of the boundary conditions, we actually increase the resolution. So particularly for wavefront shaping, if we want to do custom procedures, we want to have, nice sharp boundaries or smooth edges, but we want to be able to have measure that transition zone and accurately, and also just measure the actual, untreated or treated regions accurately without having a kind of blurring. And you can see that here on the left and the right, that as the kind of stiffer region gets smaller at the same frequency, our ability to recreate its actual stiffness properties decreases because it basically gets blurred. And so one way to overcome that is to create higher frequency waves. And so we got these air-coupled ultrasound transducers. So normally we're used to ultrasound being coupled through fluid, but we can actually couple it through air also. And so we have this kind of cone or ring type shape so we can image OCT through the middle. And you can see here that we can actually excite this up to 4, maybe even 5K. But again, one of the limitations here is, it's physics never lets us do everything all at once, is that as we go to higher frequencies, the waves actually damp faster and we lose energy. So we will gain resolution, but we can kind of lose field of view. But nevertheless, we were able to show how we can actually use our elastography methods for mapping the biomechanical properties of the cornea, particularly here in this middle case where we have the left side, which is not treated, and the right side, which is cross-linked. And we're able to effectively and very, with pretty high contrast, determine the difference between the stiffness in the two tissues, even though it's in the same cornea. And so this is pretty crucial as we're working now on more custom treatments, right? We're seeing cross-linking. And as everybody has talked about earlier, we want patient-specific therapies. So I'm going to go a little bit about the engineering principles and mechanical modeling. So we have this wave that's propagating through the cornea, but all of solid mechanics has taught us that this is not exactly indicative of the stiffness because the geometry actually matters a lot, and specifically also the dispersion. So these two equations that you'll see used a lot just take the speed of the group velocity, CG, of the wave and convert it into stiffness. However, they're based on assumptions that the thickness is infinite, and in the cornea, it's not. And we also have these spectral methods which actually take into account the thickness of the cornea. And so here with a comparison study, we're actually much more closer using these models that actually account for the geometry. However, there's one more case, is that the cornea actually has different boundary conditions because there's fluid on the posterior surface. So Dr. Han here has developed this analytic wave model that actually accounts for the finite thickness of the cornea, which is H in the equations, and it also incorporates a fluid boundary at the posterior surface, just as we have in the cornea. And so you can see here in the bottom is that we have the analytical model in red and the measurements that we make with OCE in blue, and they seem to correspond pretty nicely, and we can do a pretty good fitting here with high concordance. And from that, we can actually quantify not only the Young's modulus, but actually also the shear viscosity and see any changes in the corneal viscosity. And so you can see our results in this paper here in 2016. And beyond analytical methods, of course, we can do finite element modeling. And so Dr. Zvjetkovic did this study where he was actually analyzing the role of the limbus. So this is one area that's been mostly ignored. There's some research on it, but his results were really cool. Is that basically we take this, our OCT and OCE results here, we create a finite element model, and then we put our OCE results into the model, and we're able to actually get the biomechanical properties through the FEM modeling. And his results were really cool, and they show that the limbus actually changes its biomechanical properties with elevations of IOP completely different than the cornea and the sclera. So it seems to have a sort of kind of accommodating effect in order to keep this boundary between the cornea and sclera basically changing as the IOP changes. It accommodates for both of those tissues. And in addition to the, I was talking about the thickness, we've also studied how the different changes in the radius of curvature affect how the wave speed changes. And so we have these results here in these two papers from Dr. Han, this paper from Dr. Han in 2016, but not only the curvature, as Dr. Roberts was showing earlier, that it changes with biomechanical properties, but the wave speed, that's what we're interested in. We measure the wave speed, and so we want to see how the curvature affects the wave speed if we fix the elasticity. And so our results show that it's pretty significant. We can go from a radius of curvature of about, I think this was 10.2 millimeters, and the wave speed changes all the way up to 14 millimeters of radius of curvature pretty significantly by almost greater than 0.5 meters per second. And of course, we did this with OCE experiments and also finite element modeling, and the results are in pretty good agreement. But another thing that changes when we do refractive procedures in the cornea is the thickness. And so we did modeling on that also to show how, even though we fix the stiffness and we change the thickness, that the wave speed is changing along with that too. So these are all parameters that you have to really take into account when you're doing your biomechanical modeling. And in the bottom here, we actually did a study here where we dehydrated the cornea, basically mimicking the riboflavin addition process with indextran for cross-linking. And we dehydrated the corneas for basically this first 60 minutes is done in PBS. And after that, the 20% dextran solution was added for another 60 minutes. And we see that the cornea thins as we expect it to, but that the velocity in the cornea actually follows that thickness. However, once we did the finite element modeling, what we found is that the stiffness is actually increasing. So even though it's still the cornea tissue and we haven't done any treatment, the thickness is changing, the cornea is thinning, but in order to accommodate for that kind of loss in mass, the cornea is actually becoming stiffer. And again, we've done finite element modeling studying the presence of the fluid structure interface, just to show the importance of the boundary conditions. That using OCE here, we use a contact lens and we have a wave speed without the fluid of about 5 meters per second. And then we add the fluid and that decreased pretty drastically to 2.2 meters per second. And so that's a very stark difference in the wave speed, even though the stiffness of the material is exactly the same. So one of the limitations we have with our OCE is this is kind of what we do with our imaging here. It's called MB mode imaging. We measure at a certain point, we excite our wave, we move, we excite, we move, we excite. And so we get really high resolution results with this, as you saw earlier from the videos. However, the limitation is that we basically have to take an excitation for each measurement position. So we run into issues with time, and especially in live measurements, there's a lot of motion. So we want to minimize that as much as possible. And then because we're also holding the beam stationary and we're doing multiple excitations, we also run into safety issues. So we have to limit the amount of power that we're putting in to not exceed the maximum permissible exposure limits. So now that we have these ultra-fast lasers, we developed these techniques creating BM mode imaging, where we can do kind of single shot imaging, where we just scan very, very quickly, which we're unable to do before because the lasers or the sources just weren't fast enough. And so doing that, we do a single excitation, and because the beam is always moving, we don't have any major safety issues. And so this is our ultra-fast OCE system that we created using a Fourier domain mode lock laser source. And with that, we're basically able to create these single shot wave videos, kind of what you'd be expecting when we use something like ultrasound elastography. But ultrasound elastography, when they do their shear imaging, they have an array of detectors, whereas with OCT, we only have one. So we have to use ultra-fast scanners in order to do this. Whereas our results were very good, and they corroborated pretty well with mechanical testing. And of course, we were able to measure the increase in stiffness as a function of IOP in an in situ cornea. So like I said earlier, is that the intraocular pressure actually, as you saw, has a pretty significant effect on the biomechanics of the cornea, right? You're adding more pressure up into the cornea. So what if we're able...
I think we're close to time here, so maybe if we can kind of bring it to a conclusion.
Got it. And so what if we could measure the intraocular pressure and the corneal stiffness using one instrument? So we actually use our ultrafast scanner to create that. And basically an applanation tonometer, we're able to measure the intraocular pressure, and using OCE, and we're able to measure the stiffness of the cornea. And what we actually found is that our tonometer was actually more accurate than the rebound tonometer, but we were also able to map the stiffness of the cornea at the same time. So I'm going to skip over all this quasi-static stuff then. So this is kind of really one of the important parts that we're working on, is measuring the biomechanical properties of the cornea without any excitation, external excitation. So what we use here is actually the heartbeat. We have the ocular pulse amplitude, which I'm sure many of you are familiar with, but that's actually exerting a force on the cornea, and the cornea itself is pushing back also. And so as the fluid goes into the aqueous humor and it pushes on the cornea, we can actually measure these displacements. And so Achuth here was actually able to do that in situ in these porcine corneas. And so you can see red here is actually upwards displacement. And as the fluid is being pushing into the cornea, you saw red is that the cornea was compressing. And now as the fluid is coming out of the eye globe, it's actually decompressing, or blue is showing that it's actually getting thicker. And so we're actually able to show a statistically significant difference between the cross-linking and the before and after cross-linking. And then, of course, we're able to actually do this in vivo also. And so this is in a rabbit model, and the bottom is the heart rate measured of the animal. And you can see that it corresponds pretty well actually to the strain here on the top right. And then following cross-linking, we're actually able to measure a statistically significant decrease in the strain, showing that the cross-linking is actually making the cornea stiffer. And of course, the beauty of this is that there's no excitation, and this could be done with any sort of phase-sensitive OCT system. We're also doing some applications in the lens. Beyond that, one of the limitations is that we can't access the lens easily, so we have to use focused acoustic radiation force. And cataract.
Final thoughts?
Yeah, I'm going to skip ahead, and just thanks to all our funding sources, and yeah, any questions anybody has. And so that's final thoughts. We'll just go ahead and say that OC's coming. It's kind of maturing really rapidly now. It's been, let's see, 1998, whatever that is, 23 years. And so now what you're seeing is the development in the field is seeing clinical applications. And so all the methods have been kind of developed, and now we're kind of pushing into the clinical realm. So we need help from the clinicians to get these applications going, and kind of what sort of measurements do you guys want?